Good morning. Our project is titled A Machine Learning Approach to Wine Quality Evaluation. This is the table of contents. In this project, we will explore how effective classification and regression models are in predicting wine quality based on physiochemical data. This is our team members and contribution table. I will now go through the introduction and background. The determination of the quality of wine is important for both consumers and producers that can largely affect the demand and supply of the product. This is usually done through a blind test of sensory evaluation of the product by experienced tasters. Because of the subjective nature of sensory evaluation, there are limitations to how humans can perform precise evaluations. This opens up the interest for a more objective-based approach. Through data obtained by physical-chemical tests, properties of the wine can be modeled with machine learning algorithms to predict wine quality. As such, the aim of this experiment is to investigate the effectiveness of predicting wine quality with classification and regression models. In sensory evaluation, tasters assess the wine, and the evaluations are converted into a rating scale. The physical-chemical lab measurements, which are numerical, can then be used for training and prediction purposes based on the sensory score from the human evaluation. Classification models are more suited at predicting the category where something might fall into, whereas regression models are better at predicting a numerical output in relation to the given variable. As such, the classification models in this experiment will be used to predict whether a wine falls into a broad category, like low, medium, or high quality. The regression models will instead predict a numerical sensory score of the wine quality. Due to the nature of the dataset, the physical-chemical measurements, pre-processing is done to clean the data, normalize output, and reduce bias in training for more accurate results.
Alright, I'll be introducing the three regression models we used and how we set them up. So the first one is linear regression. It's pretty much the simplest model we have here. It basically tries to predict the quality score by combining all the features with different weights. The formula is just y hat equals w0 plus w1 x1 all the way to w11 x11. It finds the best weights by minimizing the mean squared error. That's done through something called ordinary least squares, or OLS. The downside is it assumes everything is linear, so with data that has more complex patterns, it might not do that well. Basically, it could underfit. For the setup, we used a pipeline with standard scaler. Because linear regression is sensitive to feature scale, we ran grid search CV, tuning fit intercept with fivefold CV. For evaluation, we use RMSE as our main metric. It measures how far off our predictions are on average, along with MAE and R squared. Next is a random forest. So instead of one model, this one builds a bunch of decision trees and average them all out. That way it handles non-linear patterns a lot better and doesn't overfit as easily. Since it's tree-based, we didn't need to scale the features. We tuned an estimators, max depths, and a few others using grid search CV with fivefold CV. Same evaluation metrics as before. And the last one is gradient boosting. It's also tree-based, but the difference is it builds trees one by one. Each tree looks at where the previous one went wrong and tries to fix it, so it gets better step by step. No scaling needed here either. We tuned an estimator's learning rate and max steps with grid search CV and fivefold CV. Again, same evaluation metrics.
In this section, I will compare the performance of the three regression models used in our quality prediction project: linear regression, random forest regressor, and the gradient boosting regressor. We evaluated the models used RMSE, MAE, and R-square. From the result, linear regression achieved the weakest performance with the highest RMSE and the lowest R-square value. In conclude, both the random forest regressor and the gradient boosting regressor achieved better prediction performance because ensemble linear model can capture more complex nonlinear relationship with the dataset. Among the three models, gradient boosting achieved the best overall predictive performance allows the difference between gradient boosting and random forest are relatively small. Those results suggest that wide quality prediction depends more on nonlinear feature interaction rather than simple linear relationship. This slide shows residual analysis of regression models. On the left is a residual plot of linear regression. The residual are more spread out around the zero line, which indicated noticeable prediction error across different Y quality ranges. This suggests weaker fitting ability and possible underfitting. Random forest regressor is not shown in the residual plots here, but its performance are also close to gradient boosting compared with linear regression. Random forest achieved lower RMSE and higher R-square, showing better fitting ability. However, the gap between the training and the testing performance are larger, which suggests a slight overfitting tendency. On the right is a residual plot for gradient boosting regressor compared with linear regression. The residual are more concentrated around zero, indicating smaller prediction error and more stable prediction performance. This demonstrates the gradient boosting has a stronger ability to capture nonlinear relationship within the wide dataset.
Good morning, everyone. My name is Yan Yuxuan. Now I'm talking about introduction of classification models. For classification, we compiled three machine learning models: Gaussian Navy Bayes, logist regression, and random forest. Gaussian Navy Bayes is a probabilistic model and serves as a simple baseline classifier. Logistic regression is a linear classification model that predicts class probabilities and works well for linear relationships. Random forest is a nonlinear ensemble model that combines multiple decision trees to capture more complex patterns in the dataset. Then why compare these models? By comparing these three models, we can determine whether one quality prediction is mainly based on linear or nonlinear relationships. Then, for logistic regression, we used a pipeline to combine pre-processing and model training into one workflow. First, robust scaler scales to the data to reduce the effect of outliers because one chemistry data contains extreme values. This improves the stability of logistic regression. We also used class balancing because the one quality classes are unevenly distributed. Next, we use the stratified five-fold cross validation to evaluate the models more reliably. The dataset is divided into five folds, and stratification preserves the original class distribution in each fold. Finally, we evaluated the models using accuracy, precision, recall, and Markov F1 score. F1 score was the primary metric because it balances precision and recall while treating all classes equally, which is important for imbalanced datasets. Then we are going to the comparison and analysis.
After cross-validation, random forests achieved the best overall performance for both datasets. Therefore, unlike the regression section, where all models were analyzed further, we select only the best performing classification model, random forest, for the remaining analysis. After selecting random forest as the best classification model, we apply grid search to fine-tune its hyperparameters. The highlight value represents the selected best parameters. After tuning, the model performance improves slightly. We then analyze overfitting by comparing training and testing performance. Although the training accuracy and macro FN score were very high, the test scores were significantly lower, resulting in a relatively large performance gap. This suggests that the random forest model still suffers from some degree of overfitting, meaning the model fits the training data better than unseen test data. Next, we evaluate the models using confusion metrics. Most predictions are located along the diagonal, indicating generally good classification performance. However, we can also observe that many samples from the low and high classes were misclassified as median. This indicates that median quality wines are harder to classify accurately because their characteristics are similar to nearby classes. Overall, the confusion matrix shows that the random forest model performs relatively well, but classification errors still occur mainly between adjacent quality categories rather than completely opposite classes. Finally, we analyze feature importance using the random forest model. For both white wine and red wine datasets, alcohol was the most important feature affecting wine quality prediction. Other influential features included density, sulfate, and volatile acids. This shows that chemical properties play an important role in determining wine quality classification.
For the conclusion, through this experiment, we can observe that physical-chemical measurements can contain useful information to predict the human sensory quality of wine. However, given the results, the correlation is moderate. It is not sufficient to replace sensory-based evaluations. As such, this machine learning approach is suitable to be used as a secondary method to support human sensory evaluation of wine quality. For future similar experiments, improvements can be made by using stronger machine learning models, such as the support vector regression. Datasets from different sources could also be used in the testing process to assess if the results could be generalized outside of the initial datasets. Thank you for your time, and these are the references that were used.